Hey everybody, this is Mr. Bortnick for AP Calculus AB. We're doing Unit 1, Limits and Continuity. Today we're doing the second part of our Chapter 1 review. We're focusing on sections 1.10 through 1.16. Enjoy! All right, so this is part 2 of our Unit 1 review. We've already done the mid-unit review, which covered lessons 1.1 through 1.9. If you have not watched that yet, please go back and do that first. But this is for the second half of the chapter, lessons 1.10 through 1.16. As this says, reviews do not cover all material from the lessons, but will hopefully remind you of key points. To be prepared, you should review all the packets and notes from Unit 1, including that mid-unit review that we just talked about. Let's get into it. So for number 1, f of x is equal to x plus 3 divided by x squared minus 2x minus 15. Identify the type of each discontinuity and where it's located. Well, if I'm going to find out what type of discontinuity we've got, we are again thinking about numbers that would make the denominator equal to 0. In cases like this, it is helpful to factor. So I'm going to say that this is x plus 3 in that numerator, and it looks like that this is going to be divided by x minus 5 times x plus 3 if we factor that denominator out. Now, I see that our x plus 3's would cancel. So the x value that would make that equal to 0 is going to be a whole. So I know that there is going to be a whole at x equals negative 3. And we also can see that if we plugged in 5 to this denominator, that would make the denominator equal to 0. But since this has nothing to cancel out with in the numerator, I know that I'm going to have a vertical asymptote. A vertical asymptote at x equals 5. So removable discontinuity, aka a whole, at x equals negative 3, and a vertical asymptote at x equals 5 if I graph that function. Number 2, state whether the function is continuous at the given x values. Justify your answers. So just a reminder, this is a key piece. We know that if a function is going to be continuous, we need to check 3 things. So if a function is going to be continuous, we need to know that f of c exists. We need to know that the limit as x approaches c of f of x exists. And the third one, we need to be able to say that the limit as x approaches c of f of x is equal to that f of c. All 3 of these things must be true for a function to be continuous at some point x equals c. So if I am justifying my answers like this says, I should be bringing in those particular aspects of this problem. With that said, let's start with this first one. Is it continuous at x equals 0? Well, I notice that there's these 2 parts here. The 2 parts of my piecewise function are involving this x equals 0 or around 0. So I'm going to first start off with finding out, I'll do the first rule. So our number 1, does f of 0 exist? Well, f of 0, if we take a look at this, this is the one where x is equal to 0. So I'm going to use tan of x. That's going to be equal to tan of 0, which is 0 for that. So that's the first one. Second, if we're going to show that the limit exists, we need to do this from the left and from the right. And so let's do this first. The limit as x approaches 0 of f of x, and if we do it from the left side, that's going to be equal to this part of the equation here, because it's values that are smaller than 0. So cosine of 3 times 0, which should be equal to, cosine of 0 is going to be equal to 1. And then if we do from the other side, if we do the limit as x approaches 0 from the right side of f of x, that's going to be values that are greater than 0, so that's going to be this piece right here. So then we're going to have tan of 0, which is 0. This is a problem. The fact that we've got the limit from the left is 1 and the limit from the right is 0. So I'm going to say this limit does not exist. So no, not continuous. And here's the reason. Since the limit as x approaches 0 of f of x does not exist. That is my justification for that problem, that first part of this. And so that is not continuous at x equals 0. Well, what about x equals pi over 4? Well, in this case, if we go through these rules again, we need to find out, does the point exist? So what is f of pi over 4? In this case, for pi over 4, the part that's equal to is this right here. So let's plug in. That's going to be equal to sine of 2 times pi over 4, which is sine of pi over 2, which sine of pi over 2 is equal to 1. Great. Let's do the limit from the left and the right. So the limit as x approaches pi over 4 from the left of f of x, values that are less than pi over 4, that's going to be my tan of x. That's going to be tan of pi over 2. If you do tan, not pi over 2, tan of pi over 4. If you do tan of pi over 4, that's going to be equal to 1. And then if we do the limit from the right side as x approaches pi over 4 from the right, that's going to be equal to sine of 2 times pi over 4, which is equal to 1. So we now see that the limit from the left and the limit from the right are the same, which means that that overall limit is going to be equal. And so because of that, we can now conclude, yes, the function is continuous. And why? Well, we're going to go to that third rule. We're going to say since f of pi over 4 equals the limit as x approaches pi over 4 of f of x. So yes, and the reason is not only do both of the function exist at that point and the limit exists at that point, but they're equal to each other, just like that third rule says it has to be. If I'm going to justify my answer and really show that it's continuous, you should be showing the work for each of those 3 parts. And so that's what I would expect to see, certainly on the test coming up for this. All right, moving on to number 3, find the domain of each function. So the domain of each function. Remember, for domain that we're talking about x values where a function is like defined. And so in this case, I'm looking at 2 pieces. First off, I see that the denominator cannot equal 0. So t minus 5 cannot equal 0, which means that t cannot equal 5. I also know from that numerator, because I've got a square root, that any number under square root needs to be greater than or equal to 0. So I know that t plus 3 has to be greater than or equal to 0 so so we can take the square root of it, which means that t has to be greater than or equal to negative 3. So keeping these 2 pieces together, I'm going to write this in interval notation. That's my go-to method. If we're saying that it's greater than or equal to negative 3, then we're going to say from negative 3 up to 5, union from 5 to infinity. So it's going to be all the values between negative 3 and 5. Negative 3 is included because it's got that equal to sign. It does not equal 5, and we're skipping 5. And then we're going all the numbers past 5 all the way up to infinity. Infinities always get those parentheses. Natural log. All right, we got 2 things happening in this as well. The 2 things that we remember about domain, again, that denominator cannot equal 0, so we'll start with that. X minus 1 cannot equal 0, which means that x cannot equal 1. In addition to that, we know for natural log or any log functions that the input for that log function cannot be 0 and it cannot be negative. It has to be positive. So another rule that we've got here is that 2 over x minus 1 has to be greater than 0. It has to be greater than 0. And so in this case, the only how would we evaluate this? Well, we know that if this is going to be greater than 0, since this is positive in the top, we're looking for things in the denominator that are going to be positive, right? Because a positive divided by a positive would be a positive. So I know that x minus 1 in this case also has to be greater than 0, and so x has to be greater than 1. So in this case, we already said that x couldn't be 1, and we're saying here that x is greater than 1. So if we're talking about our interval notation for this, we're going to say that it's going from 1 to infinity. And that would be our interval notation for problem number 4. Number 5, if the function f is continuous for all real numbers, and if f of x is equal to this function when x is not equal to negative 2, then what is f of negative 2? Well, if we're going to find f of negative 2, in this case, we know that if we plug that into the denominator as is, that this is going to give us 0. And so in this case, what we're going to need to do is factor. And if we factor that numerator, that looks like that's going to be x plus 2 times x plus 4. And that denominator's got that x plus 2. And so here we can see that x plus 2 and x plus 2 are going to cancel each other out, giving us that this is just equal to x plus 4. And we can then plug in our negative 2 for this. So this is negative 2 plus 4, which is equal to positive 2 for problem number 5. Number 6, let f be the function defined by this piecewise function that we see right here. For what value of b is f continuous at x equals negative 6? So if this is going to be continuous at x equals negative 6, we see that it's defined here when x is not negative 6. So that's for values that are less than negative 6 and greater than negative 6. And so this is going to be going to a particular value. In fact, if we were to look at this, looks like a problem that might have a removable discontinuity, because if we were to factor that, we would see that this is going to be, x plus 6 times x plus 2, all divided by that x plus 6. So I can see, looking at this, that this regular old graph would have a hole at x equals negative 6 as is, right? It's going to have a hole in that graph. So why is this piecewise function here? Well, we need to figure out what value of b is going to fill that hole. And so how do we do that? Well, we know that the x plus 6's would cancel. And so this is going to be equal to just x plus 2. And for the x value at negative 6, we can plug that in, and we can say that this is negative 6 plus 2, which is negative 4. So our b has to equal negative 4 if this thing was going to be a continuous function for that. Again, our original top part of this piecewise function had a removable discontinuity. If b is negative 4, it's going to fill in that removable discontinuity. There will be no hole when we take a look at this whole graph of this piecewise function together. All right, we are evaluating some limits. And these are limits, looks like I'm going towards infinity. This whole section that we're talking about here is all about vertical and horizontal asymptotes. The last couple sections of this chapter. All right, so we've got the limit as x approaches infinity for the sine of x plus 3 pi over x squared divided by 2x squared. In this case, again, when we're talking about limits going towards infinity or negative infinity, we only care about the largest exponent terms. And so the fact that this is a sine, I'm not worried about it quite yet, but I am most interested by this like 3 pi x squared and this 2x squared. Right, that 3 pi x squared, that numerator is going to grow so much faster than that x that I'm not actually even really worried about this x at all. And so if we think about that 3 pi x squared being divided by 2x squared, those x squareds essentially are going to cancel each other out. And this is going to be going towards 3 pi over 2. But that 3 pi over 2 is inside of the sine. So we then have a sine of 3 pi over 2 if we think about that limit. And so sine of 3 pi over 2 is going to be equal to negative 1. That's number 7. Number 8, if we were to do direct substitution here and plug that in, we would be dividing by 0, which means that this has got a vertical asymptote. Yep, this has got a vertical asymptote. I think I might have previously said for number 7 this is actually about a horizontal asymptote for number 7, not vertical. I misspoke if I said that earlier. But number 8, this is a vertical asymptote problem. So our question here, just a brief review for this. We remember that if there's a vertical asymptote on a graph, the graph can either go up towards positive infinity or it can go down towards negative infinity. Those are the two choices that we have. And so I know immediately, because this has a vertical asymptote, that it's going to be one of those two things. And so here I'm going to do a numerical way of approaching this. This is negative 5 from the left side, so I'm going to pick a number that is slightly smaller than that. I'm going to try like x equals negative 5.001, like that. And so if we do that, what do we have? We've got negative 3 over 25 minus negative 5.001 squared. And if we do that, that's going to be equal to negative 3 over, this is going to make this positive, so 25 minus something bigger than 25. So we're going to end up with this like negative 0.001 in that denominator. And actually, if it's squared, it's going to be like this. And so we have a negative divided by a negative, and a number that's being, a number that's being divided by a very, very, very small number. This is going to be going towards positive infinity because those negatives are going to cancel each other out. Number 9. Be careful. This looks a lot like one of our special trig limits, but those special trig limits for sine only work when this is going towards 0. Here, this is going towards infinity. And so how do we approach this? Well, we can use a little bit of our knowledge about what sine of x looks like. Again, sine of x is one of those functions that oscillates back and forth. It oscillates back and forth between two values. It oscillates between the values of y equals 1 and y equals negative 1 for that. And so if we think about what's happening here, as x approaches infinity, this is going to be going back and forth between 1 and negative 1, 1 and negative 1, 1 and negative 1. It oscillates forever. But this number is going to be getting larger and larger and larger and larger. And so essentially what we've got is we've got a small number being divided by a very big number. That tells me that this function is going to be going towards 0 for that as this approaches infinity. Number 10. We have a limit as x approaches infinity. We are talking about horizontal asymptotes here. Again, in these problems, I only care about the largest exponent terms. So I don't care about this. I don't care about the 3. In that denominator, be careful. They're not always ordered from highest exponent to lowest exponent. Our highest exponent term in that denominator is at 2x to the 5th. And so here, if we're thinking about this one, this is going to be going towards whatever 4x to the 5th over 2x to the 5th is. And we can see that those x to the 5ths would cancel each other out, giving us just 4 over 2, the ratio of those coefficients. And that's going to be 2 for problem number 10. Number 11. A couple of different ways we could approach this. What happens here? Well, first off, this numerator is not factorable. Right? This isn't a difference of two squares. This is a sum of two squareds. So I got to leave that the way it is. That means that this x plus 1 can't cancel anything up here. I can't solve this algebraically. And if I plug in negative 1 here, just the denominator is going to 0. Because if we do negative 1 squared plus 1, that's actually 2. And that's going to be divided by the 0 that we've got here from that denominator. So we've got a vertical asymptote that we're dealing with in this problem. And again, because it's a vertical asymptote, our only answer choices are either positive infinity or negative infinity. We need to know, does this thing go, which one of these things does it go to? And so since this is saying the limit as x approaches negative 1, we don't know whether they're talking about the limit from the left or from the right. So we need to take both of those into account. So here we're going to find the limit as x approaches negative 1 from the left side. If we do that, I'm going to imagine plugging in a value that's slightly less than negative 1. So like x equals negative 1 point, let's say 001. And so if we do that, that's going to be, let's see, negative 1.001 squared plus 1 divided by negative 1.001 plus 1. If we do that, that's going to be equal to 2.00001 divided by negative 0.0001. And so we can see in this case, again, all we care about here is the sign, because it's either going to be positive infinity or negative infinity. I have a positive number being divided by a negative number, so my answer for the limit from the left side is going to be negative infinity. All right, and so that's our limit from the left side for this one. What about that limit from the right? Well, for this, I'm going to try a number slightly larger than negative 1, so like negative 0.999. And so here we're finding that limit as x approaches negative 1 from the right. If we do that, that's going to be negative 0.999 squared plus 1, all divided by negative 0.999 plus 1. And so that's going to be equal to 1.99999 divided by positive 0.0001. And again, I have a positive now being divided by a positive. That's going to tell me that this is going towards a positive infinity, because a positive divided by a positive is a positive. Okay, well, I've got now a limit from the left is negative infinity. The limit from the right is positive infinity. What does that mean for our overall limit? Well, they're going to two different values. So my conclusion for this is that the limit as x approaches -1 for this function x squared plus 1 over x plus 1 does not exist. It does not exist because that limit from the left and limit from the right are not the same value. That's number 11. Number 12, the limit as x approaches infinity for this. We've got sort of two things going on here. Given that this is a negative exponent, I think it'd be easier to rewrite this with positive exponents. This is the same thing as the limit as x approaches infinity of x to the 5th over 3 to the x power. And we talked about this in our notes, but there's a shorthand way that I think about the order and how quick things go. And that's through this abbreviation called FEPL. So factorials, exponents, or rather exponential functions, polynomial functions, and logarithms. I've got a polynomial function in my numerator, and I've got an exponential function in that denominator. That exponential function is going to grow faster than any polynomial function, and so because of that, that denominator is going to get way, way big compared to that numerator. So this is going to be going to a limit of 0 for problem number 12. All right, we're on our last one, number 13. Identify all horizontal asymptotes of f of x. We've got the square root of 16, missing an x, 16x squared plus x to the third plus 5x, all divided by 5x cubed minus 8x. My only suggestion for you is when dealing with horizontal asymptotes, and specifically they're giving it a big giveaway right here. When they say all horizontal asymptotes, we need to take into consideration two different things. We need to take into consideration the limit as x approaches infinity for f of x. And we also need to take into consideration the limit as x approaches negative infinity for f of x. Because again, horizontal asymptotes are essentially synonymous with these limits towards infinity or negative infinity, but sometimes functions have different horizontal asymptotes going towards those two different directions of positive and negative infinity. So how do we approach this? Well, in this case, I'm again thinking about the fact that we have a fraction here, and I'm really only worried about the largest exponent term, so I'm not worried about this over here, and I'm not worried about this negative 8x. And so this is going to be somewhat equivalent to the square root of 16x to the 6th divided by 5x to the third. So what happens if we have a positive number, right? If we're going towards positive infinity, well, in this case, we're going to have, the square root of 16 and then a positive number being raised to the 6th divided by 5x to the third. If we take that square root, we're going to have a 4 in that numerator, and then an x to the third divided by that 5x to the third. Those are both going to have positive, the x values are positive, so because of that, these are going to cancel each other out, our x cubes, because they're the same, leading this to be a limit of 4 over 5 for x approaching infinity. But what about when x approaches negative infinity? Well, we still have the same simplification, but what we have to recognize is that we have this 16x to the 6th divided by 5x to the third. If I take a negative number, right, this is going towards negative infinity, and I raise it to the 6th power, that's going to make this positive. That's going to make this positive. But if I raise it to the third, this denominator is going to still be negative here. And so in this case, if I'm thinking about what's happening here, this is almost like the square root of 16 times negative infinity to the 6th divided by 5 times negative infinity to the third. Obviously, we can't actually cube or raise infinity to the 6th, but I'm thinking about this for an exercise. This is like the square root of 16 times that negative infinity raised to the 6th is going to become positive, so this is like a positive infinity now to the 6th. And then in that denominator, we're going to have 5 times negative infinity to the third for that. So if we take that square root, we've got a 4 times infinity to the third. And then in that denominator, I've got 5 times negative infinity to the third. Well, those infinity to the thirds are going to cancel, but I'm left with this extra negative that I didn't have before. So this is going to be going towards negative 4 over 5. So 2 different horizontal asymptotes. Again, this problem sort of gave away that there's more than one answer because they say, hey, identify all of the horizontal asymptotes for this problem, not just the one that's going towards infinity. That's it for our review for Chapter 1. Please reach out if you've got any questions. We've got that test coming up. Study, 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 and good luck to you as you start taking that. Thank you so much.